Hey guys, so we're in section 3.5, limits at infinity. Okay, so the graph that you're looking at right now shows the difference between infinite limits, which we did in section 1.5, and limits at infinity. Okay, infinite limits, as you can see, are allowed, so to speak, to tend towards positive or negative infinity. Okay, limits at infinity do not, they are not allowed to tend towards infinity. Limits at infinity will tend towards a finite number, okay? In other words, whatever that horizontal asymptote is. That's the difference between what we did in 1.5 and what we are doing right now in 3.5, okay? In other words, when you look at the second graph, limits at infinity, those dotted black lines are horizontal asymptotes. So when you find a limit at infinity, what you are finding is the equation of the horizontal asymptote. Okay, these rules are going to play a huge part in the math of this undertaking, okay? This is theorem 3.10, limits at infinity, page 193. C is some number, okay? So for example, if we are looking for the limit as x approaches infinity of 5 over x squared, because x is infinity, 5 divided by infinity is obviously going to be 0. That's like dividing 1 by a billion, trillion, gazillion. You have so many zeros there, you might as well just say it's 0. Okay, that's the idea behind that theorem. So we can look at example 1 and apply that, okay? So example 1 is find the limit as x approaches infinity of 5 minus 2 over x squared. Okay, well, since this 5 here does not have an x in it, we just leave it alone. Okay, when we look to the second term here, we are looking at 2 being the c value over x to the r, where r is 2. Now we know, because dividing 2 by infinity is going to give us 0, the limit of that function as x approaches infinity is just 5, because 5 minus 0 is equal to 5. Easy enough, okay? Now, when we look at example 2, there are 2 methods moving forward that we're going to use. So I'm going to show you how to do that. Then we're also going to look at a simpler, more clear-cut method. But then we're also going to review in depth how to do the math. All right, so for example 2, they do walk us through the mathematical method here. The limit as x approaches infinity. Now, let me just stop myself here and make a point. Right now, we're in the section called limits at infinity, okay? If you are looking at limits at infinity, x will approach infinity. You'll know that you have an infinite limit as opposed to a limit at infinity, because the limit at infinity, the x approaches infinity, the infinite limit, the x approaches a number, okay? Again, that's the difference. limit at infinity x will approach either positive or negative infinity. An infinite limit, in an infinite limit, x will approach some number. All right, so we're looking at example 2. Find the limit as x approaches infinity of 2x minus 1 all over x plus 1. Okay, well, if you put infinity here, you get 2 times infinity, which is infinity, and infinity minus 1 is still infinity. Likewise, in the denominator, if you put infinity in for x and add 1 to that, you still get infinity. Now, infinity over infinity does not equal 1. That is an indeterminate form, and we will get into that a little bit later when we start to learn about L'Hopital's rule, blah, blah, blah. But right now, we just need to know this does not equal 1. So plugging infinity in using direct substitution ain't gonna cut it. So there is another way, and we are going to examine that by doing the math, okay? We are going to divide by the highest, we're going to divide everything by the highest power of x that is in the denominator, okay? Which is x to the first. So 2x over x minus 1 over x all over x plus 1 over x. And now we're going to work to simplify whatever we can. These x's go away. These x's here equal 1. Now 1 over x follows the pattern c over x to the r. So that equals 0. Likewise, the 1 over x in the denominator also falls into the pattern of c over x to the r power. So that also equals 0. Therefore, the limit as x approaches infinity of that particular function is equal to 2 over 1, which is equal to 2. Okay? Now, we're going to do the shorter method. Method 2, follow these rules below. If the highest power in the numerator equals the highest power in the denominator, the horizontal asymptote is equal to the ratio of the leading coefficients. That's exactly what we just looked at in this particular function right here. The power on the x in the numerator is a 1. The power on the x in the denominator is a 1. So the powers are equal. Therefore, the limit is equal to the ratio of the leading coefficients, which is 2 over 1, which is equal to 2. That's what that rule means. Method 2b, if the highest power in the numerator is less than that of the denominator, the horizontal asymptote is y equals 0 always. Meaning, if we had the function y equals 2x plus 1 over x squared, for example, plus 1. The power in the numerator is 1. The highest power in the denominator is 2. The numerator is less than that of the denominator. So the limit as x approaches infinity is going to be y equals 0 always. In other words, that is the horizontal asymptote. Now for part C, if the highest power in the numerator is greater than that of the denominator. There is no horizontal asymptote. It is oblique, which is another way for saying it is a slant asymptote. And a graph that looks like that, okay, say we've got our XY coordinate plane. Here is our slant asymptote right there. We might, just for fun, throw in a vertical asymptote as well. And the way that the graph looks is just like that and just like that, okay? So that type of a situation exists when the highest power in the numerator is higher than that of the denominator. Okay, now looking at example 3, we are going to use the long division method, not long division, but the dividing by the power in the denominator for example 3, just so we can determine using the math what these limits are. Okay, and again, a limit at infinity is the same thing as the horizontal asymptote. We are going to be using this concept in the next section where we're going to be actually drawing the graphs using all of this information and all of these characteristics that we've learned so far in chapter 3. Max and min values, points of inflection, etc. Here is another characteristic, the horizontal asymptote. Okay, so we're going to abide by this rule right here that says when you do this, you will always divide by the highest power of x from the denominator, okay? So that means that everything in example 3a's function is going to be divided by x squared. So that would look like 2x over x squared plus 5 over x squared all over 3x squared over x squared plus 1 over x squared. Okay, we know because of the c over x to the r rule, this equals 0 and this equals 0. We can discount those and cross them out right away. Now we're going to do some reducing. That x takes that one away, and x squared and x squared cancel out. What we're left with here is 2 over x, and this again is the limit as x is approaching infinity, okay? 2 over x all over 3. Well, 2 over x also fits the formatting of c over x to the r when r is 1. So that means that that numerator there goes to 0. So the limit as x approaches infinity of that particular function is 0. Now remember, when we go back to our rules, B says if the highest power in the numerator is lower than that of the denominator, the horizontal asymptote is always y equals 0. Well, it just so turns out that the power in the numerator is 1, while the power in the denominator is higher than that. That's why the limit is 0. Okay, now we're going to do the math on example 3b. Now notice the powers are the same, okay? So we are going to divide by the highest power of x from the denominator, which is x squared. So 2x squared over x squared plus 5 over x squared all over 3x squared over x squared plus 1 over x squared. And again, from our c over x to the r rule, that is 0, and that is 0. Now we can do some simplifying. The x squareds cancel out there, leaving just a 2, and the x squareds cancel out here, leaving just a 3. The powers are the same. So notice, method 2A, if the highest power in the numerator is equal to the highest power in the denominator, the horizontal is equal to the ratio of the leading coefficients. On the top we have 2, and on the bottom we have 3. Beautiful thing. All right, now notice here, this falls under the rule for C here that says if the highest power in the numerator is greater than that of the denominator, there is no horizontal asymptote. It's oblique. Okay, so we're going to do the math on this one and see what happens when we do that. Okay, so we are going to divide by the highest power in the denominator, 2x cubed over x squared plus 5 over x squared, 3x squared over x squared. Remember, it's always the highest power in the denominator. I might have said numerator. That's not what I meant. Always the highest power in the denominator. Okay, again, that goes to 0, and that goes to 0. This cancels out with that. The denominator in 2x cubed over x squared is gone, and then we have 2x left in the top. So remember, we're taking the limit as x goes to infinity of 2x now over 3. Well, if we multiply 2 times infinity, we get infinity over 3. That is also an indeterminate form. Okay? That is not going to work. Okay? So, because remember, limits at infinity have to be a number answer. Infinity divided by 3 is infinity, and we can't have that here. Okay? That is not going to work. So, that's why we have an oblique or slant asymptote. And I'm going to show you how to find the equation for that slant asymptote. Okay? So, it would be the 2x cubed plus 5 divided by 3x squared plus 1, okay? While this may seem tedious and a little bit unnecessary, trust me when I tell you, starting in chapter 4, when we are looking to find integrals or antiderivatives, this skill, knowing this skill is a must. Okay, so, but in order to perform this long division, we actually have to allow for the missing powers of x under our division bar here. So 0x. Now I can say plus 5. Okay. So 3x squared goes into 2x cubed 2/3 x times, because when you multiply that times that, you're going to get 2x cubed. And when you multiply 2/3 x times 1, you're going to get 2/3 x. So we'll just fill that in. Okay. Put your line, change your signs, and we end up with negative 2/3 x plus 5. Now, 3x squared does not go in to negative 2/3 x. So the equation for the slant or oblique asymptote is y equals 2/3 x. We don't need to worry about the remainder when we do long division for this particular concept, okay? So anyway, we'll get there when we need to get there. Just be aware that the long division that we learned in Algebra 2, long division of polynomials, is not a thing of the past. Okay. As far as we go with this is going to be example 4, okay, where we are looking at the same function, but one of them is approaching positive infinity, the other one is approaching negative infinity, and we have the added fun of a radical in the denominator. So we are approaching infinity, 3x minus 2 over 2x squared plus 1. And then for b, we have the limit as x goes to negative infinity of the exact same function here, okay? Okay, so notice under the solution, they tell you that x is equal to the square root of x squared. If you take the square root of anything squared, you get back just what's under the radical, just the x, okay? So what we're doing is that means that the highest power in the denominator is just x, because we're going to be dividing by the square root of x squared. So as far as the numerator goes, we're going to be dividing by x, because again, the square root of x squared is x. And then in the denominator, we are going to be dividing the square root of 2x squared plus 1 by the square root of x squared and the square root of x squared. So we could put all of that into one single radical, 3x over x minus 2 over x all over there. Okay, now we can do some simplifying here. Okay, these x's go away. This goes to 0. This goes to 0. And those x's go away. So the limit as x approaches positive infinity is 3 over the square root of 2. Okay? Very simple. And again, the power in the numerator is exactly the same as the power in the denominator. Therefore, we have the leading coefficients as a ratio being the horizontal asymptote. Okay? Now, we could do the same thing. The only difference here is that we have negative infinity. Okay, so again, we are dividing by the highest power of x in the denominator. Okay, so I'm just going to put everything under the radical. The only difference here is that we are approaching negative infinity. Okay, so you put the negative outside the radical, and we could do our simplifying. This goes to 0, this goes to 0, that simplifies. So that limit is 3 over the square root of 2, but it's negative. Okay? And you can see on the bottom of page 196, I believe that is, oh no, you can see at the, well, kind of the bottom, page 196, figure 3.38, you've got a horizontal asymptote, -3 over the square root of 2 as x approaches negative infinity, and +3 over the square root of 2 as x approaches positive infinity. So that has 2 horizontal asymptotes. Okay, so if I can find an IXL, I will let you know what your homework assignment is going to be. Okay? See you guys.